All right. Let's do a little L'Hopital action here for our last section out of Chapter 7. Now, before we jump into our current stuff with L'Hopital, let's do a little review. Let's think back here to Calc 1 when you had in section 4.7, we started with L'Hopital back at that time, right? And if you remember, L'Hopital, you had to have that rational expression in that indeterminate form. So I would be taking a limit, because remember L'Hopital deals with limits, as x approaches a of f of x over g of x. But let's just review. I want to write it down. I said it, but let's write it. Criteria for L'Hopital is, number one, you have to have a rational expression. It has to be a fraction, right? Criteria number 2, it has to have an indeterminate form. You can either have 0 over 0, or you can do the infinity positive or negative over infinity, right? Doesn't matter if it's positive or negative, but infinity over infinity. Those are the criteria in order to just do L'Hopital, right? So once you have this rational expression, you come up with it being an indeterminate form, right? So my answer is going to be one of these indeterminate forms. If I just plug it in, if I just plug A directly in, then that's what's going to end up happening there. So keep in mind, I have to have that indeterminate form. If you can plug it in and get an answer, then go with it, right? That's just a limit. This is if the limit doesn't work when you plug it in and you have to do something extra, you go to L'Hopital. When I do L'Hopital, all right, you have to put some kind of notation out there. So the notation I use is I just put an LH in front, and then I take the limit as x approaches a. I know I've seen different notations at different times of people that use L'Hopital one way or the other. You have to put something there to show that that is what you're doing, and that's how step 1 gets to step 2, because you then take that derivative, right? And if you get an indeterminate form again, you do L'Hopital again. If you don't, then that's your answer, right? So this is just that review of L'Hopital. Now, this is the first time we've done limits here in Calc 2, and I'm going to be a stickler about this because notation is a big deal in math, and I'm writing it out. Notation is a big, all capitals with lines underneath it, deal in math. If you are taking a limit, you have to write that notation. If you don't, you're wrong. All right? Limit is an operation. Let's write that out. The limit is an operation. Keep the notation until you plug in your value. That's a G. Plug in your value. Once you use the limit, right? Once you plug that in and you're doing the operation of the limit by plugging in that value, that's whenever you lose the notation. But up until then, you keep that notation. You just simplify your rational expression, or you do L'Hopital or whatever it is, keeping the limit notation. Once you plug that value in, that is when you lose the limit notation, right? Because then you are actually performing that operation, and that's the whole point of this, right? So here is, I always like to give this example. For example, and those of you who've had me in class before know I like to say this. If I take the square root of 4, right, what is that? 2, because you do the operation of the square root of 4. So if you start off here, let's back it up just a minute. Let's try again here. What if I have the square root of 3 plus 1, right? Then you write this as the square root of 4. You're keeping the square root notation. You're just doing the simplification of the inside before you get to 2. Once you take the square root, you've done with your simplification, you take the square root, then you write that 2 there. You do not just randomly have some number 4 and then automatically work it out with a 2, right? Same thing when it comes to limits. You don't just randomly have some rational expression that equals some value. No, you have that value because of the limit. You have this 2 because of this operation of square root. Same concept. This does not equal 2. Same concept. All right? If you have that operation, work with that notation. That's what you're supposed to have. Okay, so let's do some examples here then. Let's go to blue. Let's look here. Let's look at example 1a. I want to take the limit as x approaches 0 of e to the 2x minus 2x minus 1 over x sine of x. Right? So your go-to method 100% of the time is plug it in. What happens when you plug this 0 in? Well, if I plug in a 0 here, anything to the 0 power is 1. So this is going to be 1 minus 0 minus 1 over 0 times 0, right? Which is 0 over 0, indeterminate form. And what do we get to do? L'Hopital. Now here's the thing. I'm okay if you do this part in your head, but I want you to write this part so I know that you have an indeterminate form. I know that you've done that in your head to get the indeterminate form, okay? It's just your way of proving to me that you don't just jump right into it because you're not paying attention. I want to make sure you know the only way I do L'Hopital is with that indeterminate form, not because it's in this particular section. That's not learning the math. All right? Okay, so I still have my limit notation because I'm going to do L'Hopital and take these derivatives. So I have 2e to the 2x minus 2 over, in the denominator there, we have the product rule. So the derivative of the first term is 1 times the second plus the first times the derivative of the second. Then you plug that 0 back in. 2 minus 2 on the top is a 0. 0 plus, and this is 0 times cosine, so that's a 0 in the denominator. Indeterminate form, L'Hopital again. You guys got this. L'Hopital, yo. The limit as x approaches 0 here, take this derivative, 4e to the 2x. Do you see where we're getting that? I mean, I'm just doing it because it's the chain rule, and we now know e to the x. So e to the x, the derivative is just e to the x. Chain that because you have this inside function of 2. Same thing, e to the x, e to the 2x is still e to the 2x, but I've got that 2 in front, times this 2 gets that 4. The derivative of a constant is 0. The derivative of sine is cosine. And then I get to product rule again. The derivative of the first times the second, plus the first times the derivative of the second, so that's going to be a negative, so I'm going to put a little negative sign up here, sine x. Now, I'm going to clean this up a little bit because it makes me feel better. Scoot it up. I've got a cosine here and a cosine here, so there's 2 of those. I'm not doing L'Hopital again, but I haven't taken my limit yet. So I don't put the LH because I'm not doing L'Hopital. I'm just doing algebraic cleanup. Now, plug it in. This is 4 times 1, which is 4, right, on the top, e to the 0. So that'd be times 1, over 2 cosine of 0 is 1 minus 0. So my final answer is 2. You see that? Okay, so this is the Calc 1 concept here of L'Hopital, but we're using some of our Calc 2 derivatives that we just learned in order to pull that off. So that's pretty cool, right? Okay, let's do another one. Here's example 1b. Do we have room? Oh, yeah, plenty. We have the limit as x approaches infinity of 3 to the x times pi over 2 minus the inverse tangent of x. Right? Okay. let's plug it in. That's always what we do. So if I plug in 3 to the x, that's infinity. Think about what happens to inverse tangent, right? We just did that. So what does the graph of inverse tangent look like? Do you remember? That's my graph of inverse tangent. And it goes up here to pi over 2 and down here to negative pi over 2 with my asymptotes. So as my graph goes to infinity, what does it go to up here with my asymptote? Pi over 2. So if I know this is the same thing as pi over 2, then this would be times 0. And that, if you remember back to Calc 1, is another indeterminate form. Remember, infinity to the 0? Let's make a note of this. Indeterminate form that you have to put into a rational expression. Pardon me. So you can use L'Hopital. Okay? So if you remember that indeterminate form from Calc 1, where we put it into a rational expression so that we can then use L'Hopital. Okay. Typically in this one, you have something that is to an exponent. You move it to the denominator and change the sign to the opposite, right? Let's go back to black. And that's how we get it set up. So if I take the limit as x approaches infinity here of pi over 2 minus the inverse tangent of x over 3 to the negative x. Pardon me, got a little tickle in there. When I plug in infinity now, I'm looking at 3 to the negative x is the same thing as 1 over 3 to the x. So if that goes to infinity, then 1 over infinity always goes to 0, right? So that's going to be the same thing. So if I'm looking at this, go back to black. This is still going to give me a 0 over 0, and now I can use L'Hopital. Because remember the criteria, it has to be a rational expression. You can manipulate this into a rational expression, but I can't do L'Hopital until I get that rational expression. Okay, now that I have it, I can do L'Hopital. And I take the derivative of the top. The derivative of a constant's just 0. But we now know, because of last section, the derivative of the inverse tangent. And I'm just going to write it 1 plus x squared plus 1, 1 plus x squared. It's interchangeable. Okay. And now, because of this chapter, we know how to take the derivative of an exponential with a base, right? Remember I said it doesn't show up very often, but you need to know it. Whammo jabammo, and here it is. So you have 3 to the negative x, natural log of 3, times the derivative of the inside because it's the chain rule. Bring that negative in front. Now I have a negative on the bottom and a negative on the top, so let's just take care of that nice and easy. All right. Now, here's the other thing we've got going for us. Clean this up, right? Clean this up a little bit so that you can actually see what it is that you have. You have a complex fraction. This 3 to the negative x is actually down below here. That means you have a fraction over a fraction. Multiply by that reciprocal, clean this up, and see what it is that you've got. The limit as x approaches infinity here is, pardon me, going to give me 3 to the x over the natural log of 3 times 1 plus x squared, right? When you multiply by that reciprocal, this is in the denominator. It goes to the top over the natural log of 3 when you multiply by the reciprocal, right? Okay, that's just our basic algebra. Now, let's talk about this for a second. I am okay with you going directly to the answer here. Because if you look at this and you say this goes to infinity, the denominator also goes to infinity, right? Natural log of 3 is just a number. 1 plus infinity over 3 to the infinity goes to infinity. This, whenever I'm looking at this, so you can look at this as infinity over infinity and then do L'Hopital. Or this one is going to get there so much faster than the denominator. That 3 to the x, that exponential. So because my denominator is like in a racetrack, right? Like Indy 500 fast, up that numerator is just growing so super fast compared to my denominator, it's going to overtake that. And I know that my final answer here is going to be infinity. All right. So if you can look at that and see that the numerator is racing ahead, you can make that infinity. If this were flipped, right, and the 3 to the x was down here, and you knew that the denominator was going to race ahead, right, and that puts that 0 in the denominator, then that makes that impact, or that makes that infinity in the denominator, makes the whole thing go to 0. All right, so if you can see that, go with it. If you don't see that right off the bat, then we ran out of room, so let me come over here. And we're going to take that limit as x approaches infinity here of that 3 to the x over the natural log of 3 times 1 plus x squared. And that is infinity over infinity. And I can do some, what am I trying to say? L'Hopital. All right, so we can do L'Hopital here. Now, I don't want to do the product rule in the denominator. It's just a monomial, so I'm going to go ahead and distribute this. Before I do L'Hopital, let's take that off. I'm going to take my limit as x approaches infinity of 3 to the x over the natural log of 3 plus natural log of 3. Oops, I'm going to put that x squared in front so you don't think that's an inside function. X squared natural log of 3. All right, now I can just take the derivative of each one, which makes it nice. Okay, so my numerator, the limit as x approaches infinity here, is 3 to the x, natural log of 3. This is a number, so the derivative of just a constant of a number is 0. Here, again, this is a coefficient, and I'm just taking the derivative of my x squared. So I've got 2 natural logs of 3 times x. I'm going to put it like that so you know that it's multiplied out. This natural log of 3 cancels out this natural log of 3, and I'm actually left with the limit as x approaches infinity of 3 to the x over 2x. All right, now look at this again. You can again see this is obviously going to grow way faster and get there. So the whole thing goes to infinity. If at this point you can notice that, you can write your answer as infinity. To take it all the way out, just to make sure that you see what's going down here, we can do L'Hopital again. And I end up with the limit as x approaches infinity of 3 to the x natural log of 3 over 2. Now, there's no longer any such thing as going to infinity. This is infinity over a number, so that whole thing just goes to infinity. All right? In my opinion, all of this is just extra to prove why it's infinity. All right? It's just proving the answer. That's what that is extra. I am 100% on board with you rocking the socks off that. All right, there at the end, straight up to infinity, I'm down for that. That's part of growing in your mathematical ability, is you can look at that and say, okay, that makes sense, and then go forward. All right, let's do one more here. Let's do example 1c. I'm going to take the limit as x approaches infinity of x over the natural log of x. Again, I am absolutely on board with you writing this answer as infinity. Do you know why? Look at the graphs. This is y equals x, right? This is y is equal to the natural log of x. Which one's going to get there faster? This always crosses at 1. Y equals x. Every single time, right? Every single time. So I am 100% on board with you writing this answer right now as infinity. But because we're in this section, I'm just going to prove it to you so you know that's infinity over infinity. The top gets there way faster. But if you do L'Hopital, then you would get 1 over this 1 over x. Clean that up. And the limit as x approaches infinity of x gets to infinity. And I'm okay if you put that there first because the top is obviously getting there faster than the bottom. But again, just to prove it, to make sure you understand what's going on, then that's fine. My ultimate goal for you is to be efficient. If you can see that stuff in advance, then go there. If you don't see it, then L'Hopital works outstanding. But when you start doing more and more and more of this stuff, you'll start seeing these patterns, and then you'll be able to be more efficient with your math. All right.